everyone, my name is Ian Gaffney, and this is Physics 2 Lab number 3. So the purpose of this lab is we were asked to observe how resistors and capacitors behave in real-life simple circuits. And more specifically, we were tasked with recording and the difference in time it took to charge and discharge a capacitor with different resistors attached to it in series. So the system in this lab would be the entire circuit, including all of the resistors and capacitors, and the battery, and the surroundings would be any sort of outside force acting on the circuit. The initial conditions would be that the entire circuit is completely hooked up, so all the resistors and the batteries are attached to each other with wires, but the circuit has not yet been completely attached to the other end of the battery, so that the current is not yet flowing. So in the first part of the lab, we're just doing some basic setup stuff. So I've recorded the current on both sides of the resistors to be about the same, just under 2 amps. Sorry, 0.2 amps, which was what was expected. And then if you reversed the order, then they would just be negative. So yeah. And then when I replaced one of the ammeters with a voltmeter, the voltmeter read 1.5 volts and the ammeter read 0 amps because the voltmeter took all the current as it acts like a perfect resistor. And then after that, we kind of played around with the voltmeter. So we were asked to find the voltage of, the difference in voltage of each component. So the 47 ohm resistor was negative 0.8 volts, the 100 ohm resistor was negative 1.7 volts, and everywhere else in the circuit was 0 volts. And the actual total voltage change was negative 2.5 volts, and the expected change was negative 3 volts because there was a 3-volt battery, and so it should be going down across the entire circuit, reaching 0, which did not happen. And I drew a picture of what actually happened, and what should happen is that this line goes all the way down to 0, and then we restart the circuit and it goes back up to 3. So, but that did not happen, so there was a little bit of error there. So after that, there was a couple of questions. So why doesn't the ammeter change when the voltmeter was connected across a 100 ohm resistor? Is because the voltmeter was connected in parallel, so that it was not taking all the voltage out of the circuit in series, so that the ammeter can still get a reading on the current. The ammeter, when the voltmeter was connected across a 100 ohm resistor, was 16.9 milliamps. The ammeter reading with another ammeter is connected in parallel with the 100 ohm resistor. It was 45 milliamps, and the large increase is due to a short circuit. Calculated resistance values parts of the circuit. So we were asked to find, basically based off our experimental values, what the resistance would be. So for the 47 ohm resistor, I got 42.33 ohms, so a little bit off. Same thing with the 100 ohm resistor, I got 89.95 ohms. And then the wires, I got 26.45 ohms, and then ammeters were obviously 0 ohms because they do not have any voltage drop. So for part 2 of the experiment, we were asked to find the difference in time it took for different resistors. So for a 20 ohm light bulb, it took about 5 seconds to both charge and discharge a capacitor, and we saw that through how the brightness of the bulb started off bright, and then it slowly dimmed down for both of those as the current was being either sucked into the capacitor or it was running out of current. And same thing with the 10 ohm bulb, but it was much longer. I actually got 47 seconds for both charging and discharging. So what if you change a capacitor with no resistor? Sorry, if you change a capacitor with no resistor in the circuit, how quickly would our ideal? Let me restart that. What if you charge a capacitor with no resistor in the circuit, and how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Short answer, no. But ideally, if you charge a capacitor with no resistor in the circuit, it would almost instantaneously charge and then stop the flow of current in the circuit. this would happen in real life, and there would be a dangerous and violent release of energy instead. We saw this in class a couple weeks ago. There was a huge pop when that happened. So yeah, thank you for watching, and I'll see y'all next time.